It is like saying, I know how to drive a Maruti car, right? Tomorrow basically, you have a Honda, okay. Now you can't, I mean, you don't say, oh, let me go back to driving school and take another 6-month course on how to drive a Honda, because Maruti, Honda, all basically, the fact that one is some kind of engine, the other one is some automatic something inside the engine, all that stuff is irrelevant, right? Okay, you have the steering wheel, you have the accelerator, you have the clutch, you have the brake. That's all, right? 4-terminal device. Okay, same thing here, right? It's actually easier because it is 3 terminals. You understand? So that's basically the spirit behind the whole thing. We could have chosen any device to illustrate all our circuit concepts, but we will choose something that, I mean, if you want to drive a car, right? Will you, will you choose? Okay, let me learn how to drive a Ferrari, right? I mean, there's only one Ferrari probably in Chennai, or maybe a few more, right? It makes sense to drive a Maruti car, right? Because it's cheap and it's everywhere, correct? Likewise, when you're learning about circuit design, it makes sense to learn with the Maruti car equivalent of devices, which is cheap, reliable, right, by the billions, that is CMOS. Okay, all right. I mean, and 40 years ago, if I was teaching 40 years ago, we would be talking about the ambassador, which is basically the bipolar junction transistor, right? Okay. But I learned circuit design almost 30 years ago, and with the ambassador, right? And when the ambassador went off and the Maruti came, there was basically nothing changed, right? The circuits look really pretty much the same, right? The picture of the ambassador is gone, the Maruti comes. That's all, right? Otherwise, everything looks the same. Okay. So with that background, let's quickly say now the only thing to figure out is what is this G of V1 comma V2, all right. So clearly there must be several regions of operation. So there is one region for a specific VA for a certain value of V2 for a given V1. If V2 is greater than a minimum, all right, what comment can we make? Let us call this V2 minimum. What comment can we make about I2? I2 is only a function of beyond, for V2 greater than that V2 minimum, what comment can we make about I2? It is a constant and is independent of V2, it is only a function of V1, correct. Okay. So for a couple of things first, if you recall, our amplifier therefore look like this. So now it no longer makes any sense to call this terminal 1 and terminal 2, right, and this dabba does not make any sense either, right. We can you can basically say this box looks pretty ugly. I might as well come up with my own ugly symbol for the box, right. So that is basically this symbol, and then rather than call it number 1 and number 2, right, it is like, which is like addressing you by your roll numbers, I might as well address you by your names. So like that I will call this, the symbol for this box is this, okay. That terminal 1 that which will be called port 1 is the what we will call the gate, this is the drain, and this is the source, all right. So for V1, what is the, in terms of the new terminology, what is V1? It is the difference between the gate and the source. So, that is VGS, right. What is V2? If VDS is greater than VDS minimum, then I2 becomes, what is I2 now? No, but what do you call I2? There is no 2 anymore. ID is only a function of VGS, all right, and that function happens to be, so it turns out, and this now what I am going to say now is just something which comes from device physics, and I am sure all of you are taking some device course or the other, and all the gory details of why things are the way they are covered in those courses, right. As far as we are concerned, we are only interested in the equation. If the equation changes, we do not get all flustered, it is just a matter of using the new equations. So, this ID is nothing but, it turns out to be of the form mu n C ox some W by L. I mean, at this point all these symbols, they appear like Latin and Greek to you, it does not matter. These are some parameters related to the details of the construction of the device and some properties of electrons inside the device. We do not need to worry about it, these are all given once you are given a device. Mu n C of W by L times VGS minus VT the whole square, provided the VGS is greater than or equal to a minimum which is VT. Okay. Now, let us go carefully term by term, right. So, basically if VGS is less than VT, VT by the way is called the threshold voltage of the device and is not to be confused with the thermal voltage when we use the diode equation. This and that are different. So, if VGS is less than VT, then the device is dead, right. So, it turns out that ID is simply 0 and the the device is said to be cut off or simply the device is off. Okay. Now, if VGS is greater than or equal to VT, where that basically means that the device is alive, right, and if the drain source voltage is greater than certain minimum, then the drain current is independent of the drain source voltage and is only a function of the gate source voltage, and this is basically that function. And this region of operation is what is called saturation. Does it make sense, people? So, in saturation, what is the incremental model or what are the incremental Y parameters of the MOSFET? The gate current is always 0. So, Y11 is 0, Y12 is 0, Y21 what is the definition of Y21? It was dou I2 by dou V1, right, but now I2 is nothing but ID, so dou ID by dou VGS, which is nothing but, which is called a special name rather than, now there is no 1, there is no 2. So, it is called, it denoted by GM, which stands for transconductance, right, because when you say conductance, it refers to voltage and current at the same port. Transconductance means the voltage is applied at one place and the current is happening somewhere else, right. So, that is nothing but mu n C ox W by L times VGS minus V. All right. And what about Y22? What comment can we make about Y22? Look at this equation, boxed equation in red, and tell me what is the incremental Y22? 0. Why? It is independent of VDS. All right. So, what comment can we make about the model for the incremental model for the transistor in the saturation region, therefore, is simply it is a voltage controlled current source, where the small VGS denotes the incremental VGS. So, this is gate, this is source, and this is drain. All right. Okay. Now, the only thing left is what? As far as the transistor is concerned, you know, what else do we need to know? We need to know, sorry, here I need to add another condition, sorry. VGS greater than or equal to VT and VDS greater than or equal to, we need to find what that minimum drain source voltage is beyond which the characteristics remain independent of the drain source voltage, and that just happens to be VGS minus VT. Okay. Again, why it has to be greater than VGS minus VT and so on is none of our business, right. You know, it is just it is God given. Okay. All right. So, so therefore, if you look at this picture, so this is for VGS 1. So, now let us get busy drawing these characteristics. So, this is for VGS 1, okay, and this minimum is nothing but VGS 1 minus VT. Now, if you increase the gate source voltage, what comment can you make about the drain current? For large values of VDS, what comment? So, this now becomes ID, this is VDS. For large values of VDS, what happens? The current is constant. Will it be greater than the earlier current or less than the earlier current? Greater than the earlier current. And this is for VGS 2. What comment can you make about the minimum value beyond which the current is constant? It evidently, as the our device colleagues tell us, that is greater, and below that it does something like that. Okay. All right. So, as we expected before, there is no earthly reason for that boundary between that 0 Y22 region and where it drops off to be, for that breakpoint to be independent of VGS, there is no fundamental reason, and sure enough, in this particular device it turns out that it is not. Okay. So, the only thing left therefore is to find what the relationship between ID and VDS is for VDS less than VGS minus VT. So, in the triode region, that is called the triode region, which implies that VDS is less than or equal to VGS minus VT. What comment can we make about that relationship now? It must be dependent on VDS because this is falling off. So, it just turns out, again this is one more God given equation, there is nothing you can do about it, right. It is mu n C ox W by L, where again as I said mu n C ox W by L, they are all device dependent parameters, just like how IS in the diode is a parameter which is dependent on some doping somewhere in the diode and all that stuff. Alright, mu n C ox W by L times VGS minus VT times VDS minus VDS square by 2. Technically, actually the correct model is to use is actually minus alpha VDS by 2, where that alpha is slightly more than 1, but that is basically, for our purposes we will just neglect that and use alpha equal to 1. So, this is the behavior in the triode region. All right. So, what comment can we make about the model? So, this is the model for the MOSFET in saturation, and the model for the MOSFET in triode. What comment can we make about incremental Y11? Yes, people? Y11 is 0, Y12 is capital I1 is 0, right. So, Y11 and Y12 are 0 as they were before. What comment can you make about Y21? Y21 is nothing but dou ID by dou VGS, which is dou by dou VGS of mu n C ox W by L times VGS minus VT times VDS minus VDS square by 2, correct. What is this now? Mu n C ox W by L VDS. Okay. So, what is that now? That is basically mu n C ox W by L, or let us call that GM times VGS, where GM is this quantity. All right. So, quick question, is the for a given VGS, is the transconductance greater in the triode region or in the saturation region? Why? Yeah. So, VDS for saturation, you know that VDS is in the triode region, you know that VDS is less than VGS minus VT, and therefore, the transconductance in the triode region is going to be smaller than you get in saturation, all right. Okay. Then but of course, that comes out of the math. Can you stare at this picture and tell me why that makes sense? Yes, very good. So, basically my friend there basically says that if you are in the saturation region, assuming VGS1 and VGS2 are only very slightly different from each other, what does that distance indicate? Y21 GM times delta V, correct, where GM corresponds, because the transistor is operating in the saturation region, that GM corresponds to the transconductance in saturation, right. So, if you want to look at the transconductance in triode, what are we going to do? Where are we going to look? Basically, we reduce for the same gate source voltages, or for the same change in gate source voltage, we are going to reduce the drain source voltage such that the device is operating in triode. So, basically you can see that the spacing between the two curves in the triode region is smaller. Therefore, it is evident that the transconductance in the triode region is smaller than that in the saturation region. Does that make sense? And of course, when VDS is 0, what is the transconductance? Well, the current is 0 and it is not changing. So, therefore, the transconductance is 0. Now, what comment can we make about Y22 in the is dou ID by dou VDS, and that is nothing but mu n Cox W over L times VGS minus VT minus VDS, all right, and this is often called GDS, right, which stands for the drain source conductance of the MOSFET. Okay. In the saturation region, what comment can we make about GDS? It is just 0, right. So, when you move from the saturation region to the triode region, you not only have, well, you have it is a double whammy, you not only have a smaller GM, but you also suddenly this output resistance, which was infinity before, now becomes fine. Okay. And as a final thing that I want to tell you, in saturation, GM is mu n Cox W by L times VGS minus VT, correct, which can be written in multiple equivalent forms. One way to do it is to recognize that it is the same as saying half mu n Cox W by L times 2 times VGS minus VT the whole square by VGS minus VT, and what do we recognize that part as ID. So, that is basically nothing but 2 ID over VGS minus VT. Okay. And another equivalent expression is to say, well, GM square is nothing but mu n square Cox square W by L square times Vgs minus Vt the whole square, okay, and this is, I am going to make it 2 by 2, and one of these guys I can knock off and replace this whole thing by I. Okay. And of course, the third way of is the original formula. So, Gm can be written in 3 equivalent ways, okay. 2 ID by Bgs minus Vt mu n Cox W by L times Vgs minus Vt and the square root of 2 mu n Cox W by L times Vgs minus Vt. Okay. Now, I am going to ask you a question, right. The first formula says it's the transconductance is inversely proportional to Vgs minus Vt. The second formula seems to be telling you that it is directly proportional to Vgs minus Vt. The third problem, the third formula is telling you that it is independent of Vgs minus Vt. I mean, you know what is going on? Is there some? Yeah, correct. So basically, the thing to understand is that ID is going as Vgs minus Vt the whole square. So Gm is indeed proportional to Vgs minus Vt. And likewise, the square, if ID is going as Vgs minus Vt the whole square, the square root is still Vgs minus Vt. All right. So, to summarize our discussion today, well, we figured out what the IV characteristics of a device must be, so that we get amplification in a way which is independent of the source resistance, in a way that it is unconditionally stable gain, and we get as large a gain as possible, right. And another thing on our wish list was that we also wanted the gain to be independent of RL, but evidently it is not possible, right. I mean, you know, I mean, just because you wish for a lot of things, it does not mean that they all come true, right, and this is you know, one such instance. Okay. So, we are happy with, you know, whatever we get, we move on, right. And then what did we say? Well, if these are the incremental y parameters, and given that the box has no sources of energy inside, it must be passive, correct, and therefore, if the condition that I1 equal to 0 is satisfied, then the output characteristics of the device must lie in the first and the third quadrant. So, I mean, the characteristics cannot remain, the output characteristics cannot remain parallel to the x axis for all values of V2, they must eventually dive into the third quadrant, right. Of course, I mean, you know, one way of thinking about it, one possibility is that they dive smoothly, but that is not necessarily, they could basically do some wild thing and get into the third quadrant, right. Our theory basically does not tell us that the transition needs to be smooth. It just so happens that, you know, once you say these are the characteristics I need for a device, and you go to people specializing in devices, and then they say, well, yeah, I mean, we can make not just one, but many types of devices which do this, and one such device is the MOSFET, where it in fact turns out that the transition from saturation is actually, when it goes from the first quadrant to the third one, is a smooth transition, right. And beyond that, we are you know, we are dependent, we are at the mercy of the device folks to give us work out the equations for those characteristics, because that depends on the internal physics of the device, right. So, after doing a lot of, you know, mobility, electrons, holes, all that fun stuff, you know, they say this is the equation, right. and and we say, we are happy, we do not need to know all the gory details that happen inside, okay, we will work with these equations, correct. And so we learnt what these equations were, and unfortunately there is you have to remember the equation, correct, and you remember all these formulas, right. So from 10 years from now, if you have another device, you will have another equation, another formula for transconductance, another formula for Y22, but otherwise it is the same old, alright. Bipolar, you know that the equation is different. What is that equation? I mean, of course, now the terminals also have to be different, right. You can't say I invented a new device, but it is still drain, it is still gate, it is still source, then they say what the hell have you done. So, you say this is collector, this is base, this is emitter, right. And then so what is the formula that relates now, instead of relating the drain current to the gate source voltage in the bipolar transistor, you relate the collector current to the base emitter voltage, right. And for a collector emitter voltage which is larger than a certain minimum, you see that the collector current is independent of the collector emitter voltage, not base emitter voltage, okay, all right. The characteristics look pretty much the same, right, except that there is some minor changes, and that's what I am saying, Maruti versus Honda, there is no difference, right, same steering wheel, same brakes, same clutch, same accelerator, okay, a different price tag, that is all, you understand. So, that is all that there is to, okay, good.